Hey, what's cooler than the cafeteria and gym class? Networking 101. You ever want to say to a vendor when they come in, they tell you that they use custom ASICs in their products? You ever want to say, so? What does that mean? Because, we use that term all the time, especially as a vendors. That is a very fast and loose term that we're using all the time to describe products, custom ASICs and full glass. And when it comes right down to it, really, what is an ASIC? What does a custom ASIC really mean? Well, there are a couple things to keep in mind when it comes to doing this. Man, I've been in ASIC design for a while. I don't do it anymore, obviously, tech-wise, but it's a big challenge. I mean, when somebody talks about building their own ASIC, that is a really, really, really big deal. So let's kind of divide the playing field up into players and talkers, if you will. So an ASIC is really basically a device, a piece of silicon that's designed to perform a very specific function, right? We're designing it to do switching. We're designing it to be a fabric. We're designing it to be an access point. It is a very, very specifically designed circuit, right? You probably knew this, right? This is a very kind of basic thing. It's not an ASIC is typically not a CPU. It's typically not something that we're going to buy off the shelf per se, like an Intel CPU, if you will, to run operating systems. It is designed to perform a specific group of logic functions. Now, an ASIC can be basically purchased or looked at in one of two ways. There are ASICs out there which are designed based upon what we would call an ASIC library. So you would go to, let's say that I'm a Cisco ASIC designer, and we're wanting to make an ASIC for a new access point. So I've got a couple options at that point. I can say, okay, well, look, we can either do a full design of this ASIC. We can start from scratch. We can get a regular piece of paper here, and we can sit down and we can start building out this ASIC. So that's what you'd call a full custom or a gate array ASIC, something that we are designing from scratch. It doesn't happen often because that is a very, very long development process to get that done. Or we go to what we call a fabless house, and I'll write that down if I can spell it correctly, fabless house. And what these folks do is that basically they have libraries of how ASICs are built, different types of selections. It's like buying a new car. So if I go out and buy a car, let's say I want a Corvette, I can go in and say, okay, I want a Corvette. That's my base model. A fabless house is going to have a base model. And a couple of the questions are going to be, what do you want it to do? What is it going to do? How much power do you want it to draw maximum? And what type of functions are going to be run inside? Are we going to look at like a system on a chip, what they call SIC, to actually run this out? And then we'll say, yes, we'll answer all, kind of build out these questions. And then they have different layers of pre-built type of ASICs or ASIC components, because ASICs are not, it's not basically a one-dimensional design where I'm looking at like this piece of paper here and I'm saying, okay, I'm putting all my circuits on top of here. An ASIC is like a wafer. It's multi-layered, right? I'm looking at all these different pieces, these layers, what we call substrates, that all stack up in here. And so these fab houses will have all these different substrates that work, that are guaranteed, that interoperate together, and we're going to put these into this ASIC. And then I say, okay, well, I want to actually design this custom here, and then I'll design this layer here custom here as well. And you'll see this happen a lot. It's half and half design a lot of time, or half custom, depending upon how you talk to. This is a really common thing when you're seeing ASIC is how they're building this out, is they'll use stuff from a library, stuff that's tested, and it's great. These are really good ideas because, number one, if they've got stuff in their library that works really good, it's already tested, it already interoperates, and I'm ahead of the game. It really cuts my development cycle down, and most importantly, it really, really, really cuts down my troubleshooting time when I start to go to debug on these projects. Now, another method, I told you that there's another leg of ASIC design, if you will, and when we're building out our ASIC, it's actually doing, and this is a term that the marketing folks love, it's called a programmable ASIC. And it's not necessarily, that's a very sticky term. What it really is what we call an FPGA, a field programmable gate array assembly. And FPGAs are great for prototyping. That's how we've used them a lot in design is that we'll design out our circuit, and then we will put it into a programmable gate array. It's field programmable, and so we'll program that in there, and then we can model and find out what kind of behavior we're going to get before we actually go to our metal process, where we're actually starting to lay down the ASIC. If people are trying to sell a device that's a fully programmable type of ASIC, understand that you're getting an FPGA. Now, that's not a bad thing, and it's not a good thing. It's just a thing. It's not, being in ASIC design, you really separate the two quite a bit. And what the downside to an FPGA from a design perspective, if you will, is that because these are fully programmable and they can be a lot of different things, usually they're a lot bigger. They're usually about 10x times the size. So you see some pretty big heat sinks on these. They take a lot of board space when we're designing them. They usually take about 5x more power when you're designing with these, and they do usually 2 times less stuff, if you will, because they are programmable. They have to be all things to all people. So to get that kind of flexibility, there's some things that you have to give up because they are designed to be very multi-purpose. So that's the other route that you can go in here. Now, there's some really good ones out there. Xilinx is a company actually a couple blocks down the road here. Boy, they make some really good FPGAs that'd be really hard pressed to tell the difference between a full custom ASIC and some of the stuff that they do. So I keep an eye on this space. This is really going to grow. But when people are telling you about having a full ASIC in there, then they say it's programmable. That's not this. That is not something where you go in and you're making multi-layers and you're designing that out so that chip actually supports a very specific function. It's like a tape recorder. I'm speaking my voice into it and it's playing it back what my voice is. So that's what that is. There's pluses and minuses to it, whatever you want, but just kind of understand so you know what you're getting here. Now, a couple things. When you're looking at designing into ASIC, so let's say that you want to actually build your own ASIC, right? You want to get into the field, and what does it take? How do we go from I want to build an ASIC to actually having an ASIC kind of in my hand to print it out? It's really a multi-step process. First off, we got to identify what we want and what we want it to do, right? With our want and do cycles. And then we start to really make, it's like writing a script. We kind of do a storyboard of what we expect that to do. And then we go to another function called RTL. RTL is the piece where we actually start laying out the logic to seeing how all this traffic is going to flow, right? We start building these components in. We start laying all that stuff out. And we do that with what's called an HDL, hardware descriptor language. And there are 2 big languages to doing RTL. There's VHDL, and then there's Verilog. I'm a Verilog guy myself. It's what I've used for years, and I think it works pretty good. Verilog is kind of one of those programs that if you know really any other programming language, you can pretty much be pretty darn proficient in Verilog in about a week if you already understand how to program. It's really pretty common sense, but it really tells how the logic works in the board, right? Make sure everything's going to kind of work like we want it to work in that cycle. After we go through determining what that is, we go to another function, no matter what your programming language is. It's called netlist. Netlist is where we are doing all our simulations. We're electronically, kind of virtually, if you will, electronically hooking everything up. And we're making sure everything works. All the traffic is flowing like it's supposed to, and everything is supposed to be happening, and everything's transferring across. It's our full simulation of this product. Once we pass netlist, then we go to the photography, the photography where we're actually taking pictures of the dies. Now the die itself, when you're looking at making an ASIC, it's the die is what you're really making, because we want to stamp a whole bunch of these out all at one time, right? So we're printing our circuit boards on this die so that when they go through, they can stamp. When people have pictures of ASICs and you see those like, multi-square blocks with all these lines going everywhere and stuff like that, that's the die marker, right? That's the photography we're using to burn that ASIC in, that lithography that we're using to actually burn that in to make this die. And what is most important about a die is really the size. How many microns can I make that? if I can make that like 19 or something like that, microseconds, if I can make that like 19 microns, then you've got a really small die. The smaller the die, just like a cell phone, the smaller the die it takes, the less power it takes to run it. The less power it takes, the less energy it takes, the less everything, the more greener it is, and the more components I can put in here. Typically, the thicker dies have a whole lot more diodes on those and a whole lot of capacitors on here. Your caps, when you're making these things, are what generate all the heat and really cause those things to get really darn hot when you're designing them. We're getting way too deep in the woods here when it comes to ASIC design. I just really wanted you to understand that when folks come in, when vendors come in, they start talking about, we've got a full custom ASIC in here, really what that means and really what goes into that. There's positives and negatives to it. There's not that many folks out there, including Cisco, that actually make their own chips. We typically do it what we call fabless, where we actually have the libraries that we talked about here, where we're designing all that stuff out. And then we get everything working, prototyping like it should, and then we send that to a foundry or what we call an IDM, and they actually build and design, or they actually, make the chip itself, the physical chip, and then they put it into this piece here. It's called a package, right? It's what you have, the visible representation of it. The ASIC is really small. It just kind of fits right here in the middle of it. You package this out. These are pins. So people say how many pins it has, for input and output lines, that type of stuff. But that's what that really amounts to. You can buy these off the shelves, whatever the case may be. But ASIC programming is really a lot of fun. It's very cool. It's something to really dig into. If you're really wanting to advance your career and kind of really get into if you're real super mega anal retentive like me, and you really like getting to the nuts and bolts of not moving protocols around, but moving bits inside of small pieces of silicon, this is definitely the career for you, man. ASIC design is really cool. Understand programming, you can jump into Verilog pretty quick. But this is good stuff. It's a lot of fun, and hopefully it helps you understand ASIC development and ASIC design a little bit better.